Hello and welcome to this presentation about Eclipse optics and optical design of microscopy illumination. My name is Olaf von Hofsten and I work for Eclipse. Eclipse is a consulting company in optics and we are 19 consultants working in a variety of projects. We're all project developers, but Eclipse doesn't have any products of their own. We're just the people working here. The areas of expertise that we have is optical design. We work a lot in ZMAX, doing imaging systems, microscope objectives for cameras and other imaging solutions. We also work with lighting, non-sequential design of optics, waveguides, light guides, using an LED to illuminate a surface in as aesthetically pleasing way as possible. A third thing we do is optical metrology and sensing, and here I think of this in a broad sense, measuring different things like distance, concentration of something in a gas, measuring any spectroscopic content of a fluid or something. The fourth thing we do is camera technology, and we're very strong here, I would say, where we have knowledge about the whole chain from taking the picture until analyzing it. Business areas that we work in is usually areas where you can afford to have a consultant working with an optical solution. But many of our customers do not have their own optics department. But we are spread out with consumer electronics, automotive, energy and environment, medtech, of course, safety and surveillance, and industry. You see here a system from Mycronic, which is a customer of ours. Okay, so now I will talk a little bit about optical design for microscopy illumination. And this is a type of project that we do a lot. If you want to integrate a microscope into your product, then you usually do not have, doesn't really make sense to make your own microscope objective, but it does make sense to do your own illumination. So the goals of this design is to efficiently deliver functional light to the specimen. This is the most important. Then you want usually to match or overmatch the NA of the imaging objective, and at the same time create a homogeneous lighting of the specimen. So you need to know a lot about microscopy to do this design. Many of the methods that we have today end up using high power LEDs. This is a little bit new in this area, since a lot of the old designs were using incandescent bulbs. And with high power LEDs then comes also a spherical optics. This can be used to create a compact design. And then you also need to design and optimize apertures. So the first type of illumination that you may know of is critical illumination, where you image the source onto the specimen plane. So if your LED is on the left here, then these different colors represent different areas of the LED, and you will image it onto the specimen. The drawback of this solution, of course, is if you have any structures in the LED, if you have any inhomogeneities there, then they will also turn up on the specimen, which you do not want. So you need to diffuse this in some way or smooth it out. And another problem with this is that your NA of the illumination will be dependent on where you are in the specimen, and also therefore also the resolution. but this system is short and compact, which is maybe the only good thing. So this is usually not recommended. What you should use instead is Köhler illumination. You have a picture of Herr Köhler here to the right. He's old, but when he invented this type of illumination, he was only 27. So what you do is you take your LED and then you image it onto the back focal plane of another lens. And this lens system will redirect the light towards the specimen, but now the specimen will be in the Fourier plane of the source, and all the source homogeneities will be evened out. And in this way you can also create high angles of incident illumination to optimize the resolution, and there is plenty of room to put in apertures so you can optimize. Phase contrast can also be used with this. Then you, on your back focal plane, you also use a ring. You can see it here in the orange in the top right image. In the lower left, you can see it as green light coming out of this condenser annulus. It's redirected down to the specimen, which illuminates the specimen evenly. And the light that's not scattered will end up on this phase shift ring in the back focal plane of the microscope objective. So this light is phase shifted compared to the scattered light, which will make them interfere in the image plane. And this, of course, being able to see phase contrast is a very big advantage for biological samples, which are usually do not have any absorption. And okay, and third way to do this is to use fluorescence. And a fluorophore can be excited by one wavelength and then emit another wavelength. So you can see it here. From the left, you have an excitation source, which is reflected down through the microscope objective onto your specimen. The specimen will then emit fluorescent light. Some of the excitation light will also be scattered back, but this will be stopped by the emission filter and the dichroic filter. So what you get is only the fluorescent light that goes back to your camera, and you can then now label specific molecules, and this is a very big thing in biology. Just going to show you some of our references that we have worked on in this area and what we offer. So we can offer everything from workshop to concept development, optical design, or a full turnkey system. We can also do tests, verification, or design of that, and we'll give courses and technology updates. Thank you very much.